Yeah, I will start with binary classification because that's it's all about in Cinderella. So there's this famous quote: "The good ones into the pot, the bad ones into your crop," and from the fairy tale Cinderella. And what's basically referring to is when Cinderella is sorting peas into basically two categories, good and bad ones, and this is essentially a binary classification, and therefore we came up with the name Cinderella. And here you see a small figure where we use Cinderella to classify 2D class averages. You start with some set of class averages that contain bad and good class averages, and you want to separate them into good classes and into bad classes. And you can do that with Cinderella, but you can do more, like selecting micrographs, good or bad micrographs, or selecting sub-tomograms. And I will talk about all of these three cases, but before I show you the applications, I would like to talk shortly about a few technical details in Cinderella. So we are using the same backend network as Cryolo. So what does that mean? Convolutional neural networks are often divided into this feature extraction part and the part that does the classification or the actual object detection. And Cinderella shares the feature extraction part with Cryolo. This has one advantage, and I will come back to that advantage on a later slide. But yeah, this network worked very good for Cryolo, and therefore we didn't saw any point why it should not work for the 2D classes. All right, during training we have an online augmentation. We flip the images, we rotate the images, we add Gaussian noise or remove some pixels and replace them with a mean value. All that is implemented to avoid overfitting. Yeah, and that's essentially what might be special about Cinderella. Other than that, it's just a binary classification and pretty much straightforward. All right. The first thing you might want to do is train a model for your specific case. And what you have to do is you just create two folders, and you might want to put good micrographs and bad micrographs into the respective folders, so good or bad. Or you can even, in case of 2D classes, you would put stacks of 2D classes into the good and into the bad folder. And then you specify that in a configuration file. And an example for this configuration file is given on the right side here for 2D classes. I will start with the first entry, which is the input size. Here we use 75 times 75 because our class averages are of that size. The next one is the batch size, because the batch size is essentially how many class averages in that case will be processed in parallel in the network. And as the input size is quite small, we can use a batch size of 32. But this depends a little bit on your memory your graphic card has. So it might be, if you run into memory issues, that you have to reduce the batch size. It also depends on the input size. So, for example, if you try to train Cinderella for micrographs, then you are not using a size of 75 times 75. You would rather use an input size of 512 times 512. So it's bigger than 75, and therefore we have to reduce the batch size. And typically 5 to 8 is working well with a graphic card that has, let's say, 8 GB of memory or 11 GB of memory. All right. The next two entries are the good pass and the bad pass. these are just the passes to the good directory and the bad directory. Then you have one line pre-trained weights, and it is empty here. And now this is in principle the advantage we have because we share the same backend architecture with Cryolo, because you can now use the general model in Cryolo, or the general model of Cryolo, as pre-trained weights for Cinderella. And it turned out that this is a much better initialization than just initialize the network randomly, and it leads to far quicker convergence than not using the pre-trained weights. The next entry is save weights name. This is essentially the final name of your model. And then you have 3 more entries. Learning rate, that is a multiplier of your step size during training. I never change it, to be honest, so you can stick to that number for your data set as well. NB epoch are the maximum number of epochs. Typically, you don't reach this maximum number because this next or the last entry is NB early stop. And as soon as Cinderella notices that the validation loss does not improve 15 epochs in 15 consecutive epochs, it will stop the training. All right, the second step after you configured your configuration file is to run the training. And at the end of the training, you get your model, this model.h5 file here. Okay, and then you can apply it in several ways. One situation where you might want to use Cinderella is for the classification of 2D classes. And here are a couple of examples of good classes and bad classes. We trained a pre-trained model that you can apply on new data sets, and it's based on roughly 2,500 bad classes and roughly 3,800 good classes. The training is quite fast, so after 3.5 minutes it's done, and we get a validation accuracy of 96%. So to run the actual prediction on a set of new classes, you can just type sp_Cinderella_predict. You specify the stack that you want to classify with -i, the model that you want to use with -w, and the output folder where you want to write the results with -o. And it might be that you want to change the default confidence threshold, which is 0.5 to something higher, let's say 0.7. Then you need the -t flag. And in case you want to use another GPU, you can specify that with a -- GPU flag. Okay, Cinderella will then classify your input file, and it will write 3 files as example. One is the stack with your good class averages. One is the stack with your bad class averages. And the last one is a file called index_confidence, and it contains the index of your class in your input file, together with the confidence that this is a good class. Yeah, and that's it, basically, for 2D classes. Here is an application for micrographs. It's an actin-myosin dataset, and I show you a couple of good and bad micrographs. So the good micrographs show clear filaments on good eyes, and the bad micrographs show either a lot of contamination or crystalline eyes, and you want to sort it. You want to sort them out, because you don't want to do it manually, right? So we trained a model on 100 bad images and 100 good images, and after 3.3 minutes, we got a model with a validation accuracy of 100%. Now I have to say that the validation set only contains 30 images, so the actual validation, the actual accuracy might be lower, but at least it indicates that you got a pretty good model. All right, to run the command, it's an analog to the 2D classes. You just specify now a folder with your micrograph as input instead of a specific file for classes. And as output, you get, again, 3 files. A good .txt file, which contains the file name of your good micrographs, a bad.txt file, which contains the file names of the bad micrographs, and a file name _confidence, which contains the file name in one column, and in the other column, the confidence that this is a good micrograph. Okay, that's the last, or no, this is the third application I would like to show you. Here, it's quite in a beta state for the support for sub-tomograms, because right now Cinderella only supports 2D images as input. I plan to add support for 3D, but right now it only supports 2D images. And therefore, before we can create training data for sub-tomograms, we extract the central slices of those tomograms. And we then took 28 good slices and 28 bad slices and trained a model for it. And we get an accuracy of 91%. Again, the validation set is small. It's just an indication that you got a good model. And if you apply it to your stack of sub-tomograms, you will get 2 new stacks, one containing the good and the other one containing the bad sub-tomograms, and a third file called index_confidence, which contains in one column the index of your sub-tomogram, and in the other column the confidence that this sub-tomogram is a good one. Other than that, the prediction, so to run it on another set of sub-tomograms, it's the same as for micrographs and classes. You just have to specify your input, your weights, and an output folder, and you can run it. Okay. This slide shows the reason why we initially developed Cinderella. Because in our software package Swire, we have, let's say, a pipeline set up where we can set up a complete pipeline. It will run the complete processing in an automated way, and that you end up without user intervention with a, in the best case, high resolution structure. But in the step between the initial model, the step between 2D clustering and the initial model, you need a manual selection of 2D classes, the good 2D class, because you want to sort out the bad ones. And that was the reason why we developed Cinderella, to do that automatically, that we don't need user input at this point. All right. And another application that we are working on right now is the automated training of Cryolo for any data set. And this works as follows. You start with your data with some set of micrographs and a general picking model that comes with Cryolo, which is basically pre-trained and works on new unseen datasets as well. But of course, it might be that that it does not perform too good, or it misses some particles, or it picks contamination, or something like that. And therefore, we have this feedback loop. You start with Cryolo, it picks some particles, and our 2D classification tool ISAC will find a stable set of 2D classes, and Cinderella will then select those good classes, extract the coordinates, and these coordinates are then used to retrain Priolo. And this is working very good for many cases. We have tried it. And even if you start with highly contaminated picks, let's say only 20% of good particle picks, after 2 rounds, you end up with a very good picking model. And yeah, that's basically it. What I can tell you about Cinderella. You can find an extensive documentation and tutorials on our website. Everything that I explained you in this presentation is also on the website, a step-by-step tutorial how to apply it on micrographs, on classes, or on sub-tomograms. Yeah, check it out. And I would like to thank the complete Swire team, and especially the head of our department, Stefan Raunser. And of course, the complete Raunser crew, because without them, I would not have all of the training data I need. And that's already the end of my talk, and maybe some of you have questions.
Great. If anyone has questions, we're a good size today, so I could go ahead and unmute everyone, or you could send me a chat and I can unmute. You might be able to unmute yourself also. So, I mean, I can kick it off with some sort of general questions that I have about, I think users want to know, like, should they train their own models on their own data, or can they use the models that have been trained, for both particles and for micrographs? It seems to me that maybe micrographs would be easier to use a general approach, but I don't know why I think that exactly.
Yeah. So we right now we only provide one general model, and this is a general model for 2D classes. This general model has one limitation because it's only trained on ISA classes right now. So it might be that if you apply it to reliant classes, for example, that it does not perform that well. But all of the training data is available, or most of the training data is available. I cannot upload all of them because some of the training data is confidential. But most of the training data is available and can be used to train a new general model that you want to use at your place, for example. For micrographs, we don't provide a general model yet. We currently gathering training data to do exactly that, to train a general model for micrographs. And yeah, it's always a little bit complicated to decide what is really a bad micrograph and what is a good micrograph, because sometimes a bad micrograph for project A might be still an okayish micrograph for project B. So yeah, we try to at least to train a model that classifies out the clear cases like crystalline ice, for example.
Yeah, I can imagine with the feedback loop that you showed before that even a bad micrograph, after a few iterations of that loop, might yield pickable particles. There may not be a lot, but it might have some, right?
Yeah, might happen. True. So, yeah.
So, are you accepting donations of either pre-sorted micrographs or training data to help improve your sort of global models?
Definitely. And if you go on our website, we already I have specified a couple of links to an own cloud directory where you can upload your data in case you want to share it. But of course, you can also just send me an email, and I set up a folder where you can upload your data confidentially. And yes, of course, I would definitely accept those donations.
At what point do you think that the data would be kind of enough? I guess it would have to cover all detector formats and particle sizes and all sorts of. So there's probably a lot of room for improvement. But
You mean what is the upper limit of training data that I would need to generate the perfect general model? Is that your
Well, I
question?
guess, perfection would be hard, but I guess, within reason, the most computationally feasible that you could arrive at a model that would be sort of the best performance for, most cases.
Mm.
Given, there's still a lot of K2s and K3s out there in use. People are sort of using both at the same time, and then, you know, plenty of Falcons and other detector different formats that would be
Yeah.
So you need to cover all of those, and then so I don't really know.
Yeah, it's super hard to guess. I also don't know. I cannot come up with a number.
But you're still more data is welcome.
Sure. I mean, right now, 20 data sets for the 2D classes, it's not too much. So I still guess that there are some problems with different shapes that might, or very strange shapes that proteins might have. So I think, of course, there's definitely room for improvement. But this is what we can provide right now from our side, and hopefully at some point we will come up with a public data set that we can use for training.
So there was a question. How do you distinguish between the good and bad classes for your training data set, and how many particles sort of minimum would you require for that training?
Mm-hmm. So these are two questions. Let's answer the first one. How do I decide what is a good and what is a bad class? So for our training, for bad classes is quite, let's say there are clear cases like pure contamination or pure background. So you can easily add them or clearly add them to the bad classes. There are other cases where it's not that clear, and I think that Cinderella should include all of those classes that you would accept if you would not know the protein. And this is a kind of thinking we apply if we sort the micrographs for or the classes for training. Would I use that class if I would not know the protein? Yeah, and the number of the second question was the number of classes that you need for training. And in our department, some users, if they really know the protein, they start generating their own models, and typically they train it on 100 examples of good classes and 100 examples of the bad classes, and this might be this is typically enough. But it's of course a little bit project dependent.
Mm-hmm. Yeah, here's a question that sort of gets to that project dependence. Have you tested 2D classes with rod-like particles that have long side views and then very narrow dot-like views when you're sort of looking down the particle?
Yeah. So in our lab we do a lot of processing of actin, and therefore yes, we have at least filaments. Maybe not particles, but filaments are contained in the training set of Cinderella. But yeah, dot-like top views could be problematic. I don't think that we have so many training data for elongated particles right now. So that might be a weak point of the current pre-trained model. But as I said, we are open for training data.
Yeah, this is we need more and varied training data to start to.
Sure. You only get a generalization if you have a big enough training data set that shows all of the or most of the possible shapes that the network can start to generalize. Okay, this is a feature I have to look for.
Here's a sort of interesting question. If you had a 3D structure, could you use that to generate some views that you could use for training? If you had a model.
Yeah. Yeah. So sure. In principle, you could generate particles, and then you run 2D classification on them, and add that to the training data of the model. Sure, this would be definitely a possible way to generate training data.
Yeah, that's interesting because then you could just generate a general set from the PDB.
Sure.
Or something. Yeah.
Sure. Yeah.
That's interesting. So the pipeline is coming. Is that going to be part of the Transfire project?
Yeah.
Yep.
So in our internal version, it's already part of the Transfire project, and yeah, with the new as soon as we finish the work on this idea, it will be available for everyone. Sure.
Wow, that's great. Great. Well, with that, any other questions? I think if anyone has any interesting or pre-trained data sets they'd like to share, be sure to reach out and
please
share those. And great. With that, thank you very much. Look forward to seeing the developments on the pipeline. I know everyone's looking for ways to sort of get on-the-fly results, particularly 2D classes, so they can see not only is their sample great, but is their microscope working properly, and are their grids good? It's very valuable. It's a nice way to make sure that your microscope time is being used effectively. You don't collect a day's worth of garbage before you find out that your classes were no good from the beginning.
Yes, true.
So that's really great. And and thank you everyone for joining.
Thanks for the invitation.
Great. Take care. Bye.
Bye-bye.